Welcome to another episode of the Concrete Logic Podcast. And today I have Bob Higgins back on the show. Folks like to call him Concrete Bob. Isn't that your nickname down in Australia? They called you Concrete Bob when you were down there?
In Ireland, Germany, Switzerland, Australia, and some places here in the United States.
Yeah.
It's some of the people here in the U.S. use Concrete Bob in a derogatory way, but it's because
I think to me, if you're associated with concrete and you concrete in your name, then you're doing something right. But there's Bob's going to go over a few things for us today. So we're going to learn about the challenges that we're having with older concrete as far as durability. So when we say older concrete, we're talking about 10 years plus. Also, we're going to talk about why with the new concrete that we're dealing with now, how we can't properly cure that concrete the ways that we know of curing. So we got to come up with new ways of curing concrete. And then the last thing we're going to go over, if we got time, is the differences in today's concrete versus older concrete. Before we get Bob started on that today, just want to remind you all how you can support the podcast. There's several ways. The first way is if you enjoy the podcast, please share and with a colleague or a coworker. I've had people reach out to me on LinkedIn asking how they can help, and that's the first thing I tell them. Just share it and get the word out. The second way is if you go to the website, concretelogicpodcast.com, there's a couple ways that you can get a hold of me. There's a contact link at the top of the webpage. It just says contact. You just click on that. And then at the bottom right-hand side of the page, there's a little microphone, and you click on that, and that's they'll record right over the computer. It's like leaving me a voicemail. So those are the two ways to get a hold of me. And what I'm looking for from you is guest or topic suggestions, things that you want to hear on the podcast. The next way you can help out is there also on the Concrete Logic Podcast homepage, www.concretelogicpodcast.com. There's a donate button. You click on that and you can give any amount. And I'm serious when I say this. Any amount is totally appreciated. It just tells me you appreciate what you hear on the show and helps pay for the things to keep the podcast going. And then the last way is if you're one of those people that are like, hey, Seth, I want to send you money, but I want to get, something back or some kind of service back. With that in mind, what we came up with is Concrete Logic Academy. So if you go to concretelogicacademy.com, you can go on there. You can join several ways. You can take one-off courses, or you can join. There's monthly memberships as well, annual memberships, however you join. But it's essentially a community that everybody can go in, join, and we can talk about whatever we want. We can take courses. We got quizzes in there to take. So it just reinforces what we're talking about on the show. Same topics, maybe things that you won't, things that won't just be discussed at other, associations or industries in the concrete business. So jump on there. We got a couple dozen people already in there, so feel free to join those guys. And I think that's it for now, Bob. So we can jump right into what you want to talk about today. So you want to roll into the challenges we're having with older concrete.
Yeah, I'm going to give an example. At the beginning of 2023, I was given a seminar to an installation, flooring installation group up in San Leandro. And as I was getting towards the end, one of the installers said, I want to bring up something that confuses us, and it continues to confuse us, and we don't know why this is happening. I said, okay, go ahead. He said, why is it that older concrete, we will do moisture tests, and the moisture tests are consistently lower than newer concrete, but we have more flooring failures with older concrete than we do with newer concrete? I said, that's a great question, because I had to learn the hard way. I went through about 20 years of that before I finally, I got knocked in the head enough times to realize, okay, there's something going on here. So I did some analysis on it. And about 30 years ago, I did a hypothesis that the salt buildup towards the surface of the concrete can be extreme enough to where it can create sweating slab syndrome. And although we didn't call it that, it would just cause a dampening effect. I think Peter Craig actually coined that term, sweating slab syndrome, later on. But when I came out with that hypothesis, boy, I was attacked from all sides. Oh, that's stupid. Concrete is like a big sponge and everything's stable. And well, that's not true. What was really nice is I got vindicated later on, but I'll finish this story. So anyway, I told him, I said, it tends to build up towards the surface. Now, if you have a coating or even a hard trowel surface or a curing compound on there, what will happen is moisture wants to move to the cool side. So the moisture, if the concrete is consistently cooler in the center, which it normally is, compared to ambient conditions, the trend is to move into the concrete. Well, such as salts tend to get more active as it gets warmer. So it wants to migrate towards the surface. So we've got this disparate activities going on, but what will happen after time, it just kind of does this, levels off. It just reaches a dynamic equilibrium. But then when you strip the coating off, now it's exposed to a brand new moisture source, which is the ambient air. And they just looked at me and said, how's that possible? I said, well, the salt, think of a calcium chloride test. You put salt on top, it collects water vapor into the little dish, and then you measure it. Well, just think of that. There's salts in the concrete. They're pulling moisture from the air rather than from the concrete. So that's what's going on. Well, they weren't quite sure they believed it until about 3 months later. There was this company that went out there to go show them their moisture meters. And so, well, we're going to show you how to use them. It's the exact same location, which was perfect. With a 42-year-old slab, it's out in the warehouse. They tested over the curing compound, and it was 1.9% moisture content. So they ground it off, tested immediately. It was 1.9%. Well, they left and came back somewhere between 10 and 15 minutes later. They didn't keep track of it, but they said it was a very short period of time. They put the meter back down. It went all the way up to 4.3. So they called me immediately and said, how has this happened? I said, well, that's the salt I was telling you about with the older concrete. That it will, you expose it like that, it'll attract moisture from the air. I honestly didn't think it'd be that dramatic and that quick. Where the vindication came in, last year, there was a European concrete conference, and there were studies, oh my God, in the seminars and everything else, you kind of had to pick where you were going because there were literally 200 or 300 seminars that were going on during this incredible amount of concrete information being shared. And this is over in Europe. And anyway, this one company based out of the United States, Weston Yeltsin, showed on the September 24th, 2024, that salts tend to accumulate towards the surface of the concrete as it gets older, and that's one of the causes of sweating slab syndrome. So the hypothesis I gave over 30 years ago, this 20-year study confirmed it. And they did not know I was the originator of it. And they had no idea of other data that was coming in. They arrived at this independently, which to me is more important because there's no collaboration. When you arrive at a similar, almost identical conclusion using completely different approaches, that to me is the most compelling thing you can do.
Yeah.
And then thirdly, I was giving a seminar to this group. They apply epoxy coatings in commercial and industrial settings. One of the epoxy manufacturers now recognizing this with older concrete, and they're now and they're also seeing this in some of the newer concrete. They test it first, and then with the older concrete, they normally recommend that you shot blast it. Well, they have to shot blast as deep as a 1/4 inch under some circumstances. And without doing that, they won't give a warranty for their epoxy. But when they do this, they're not having failures. So that's very compelling. Well, they discovered the same thing we did, the collection of salts towards the surface.
So they're going down a 1/4 inch because they're taking all the salt off the surface.
Well, I don't think they need to do that deeply. But unfortunately, concrete is very inconsistent, especially in the surface. And it's been getting less and less consistent as we go, where the newer concrete is now starting to look more like older concrete, it's really confusing the separation. There used to be a fairly clean separation. The concrete's 5 years old or less. This is pretty much what you could see, and 10 years and older. And then there's that gray area that was between 5 and 10 years that could go one way or the other, but now it's all mixed up. You can get concrete that's a week old and can start having the same issues as you can see in older concrete. But with older concrete, a lot of the details that we should have been taught are not being taught. All concrete goes through hysteresis. I'm not going to take a dive into these things because that's a rabbit hole we don't want to go into in this podcast or some of the other technical things I'll be telling you about. But concrete also tends to be adiabatic, which is another technical term, but I learned that when I looked at this study done in Florida by the Solar Energy Commission. They wanted to find out what was going on and how they could optimize the rate of heating and cooling control in residential buildings. So they took these side-by-side homes in Cocoa Beach. This is fairly recent, 2015, 2016, and they found that the center portion of the concrete tends to be adiabatic. Well, adiabatic means the temperature doesn't leave or enter. It stays constant. That surprised me. But when I correlated it with another study that was done in 1974 by the Army Corps of Engineers, they were testing concrete that was going to be used for these nuclear vaults and containment. So they were subjecting the concrete to 150, 160 degree temperatures, and they would do it from both sides. One of the key takeaways I saw in that is they referred to that as adiabatic. The center portion of the concrete, the moisture volume never changed. It didn't move because there's a dynamic that goes on that we're not being taught. Water tends to move to the cool side. Temperature controls water movement more than anything. People say pressure, but the pressure does not exist without a temperature change unless there's a forced outside environment. It has to be a forced outside environment. It has to be pretty significant. Otherwise, that won't happen. So what happens when you're drying out concrete is going through that zone, we have gradients of the concrete that tend to isolate in the top 3/4 of an inch to 1 inch of the concrete. This didn't happen so much in the past because there's stuff that we put in the concrete now and the finer grind that is creating these issues where it's getting worse. We thought that with a finer grind, because if you go back to 1920, they had a very coarse grind of concrete, and if you just fogged with water, say once or twice a day for 3 days, you get really good concrete. Well, when they started grinding the concrete finer, they found that, wow, look at the great strengths we get. And so they targeted the 28 days. I'm not quite sure why they picked 28 days. I've never really been able to convince myself that, okay, this is the genesis of that. I'm not quite sure. But the 28-day thing came up. So let's get 3,000 PSI at 28 days, and that's great. Well, what happens when they were using the finer grind, they found, hey, we can use less cement to still hit that target. So by 1980, there was in Concrete International Magazine, which is an ACI publication, an author by the name of Ed Monroe, who was a concrete technologist out of England, pointed out that with the finer grind cement, if you took these concrete with a coarser grind and put it side by side with a 1980s concrete, and they're both 3,000 PSI, the 1980s concrete would be 5 times more permeable. And also it generated more heat. So it was requiring longer periods of dampening with water to help cure the concrete, because when it heats up, cement tends to accelerate and set, then it becomes retarded. Now, those links have never been established, which time and time again, I read study after study, and it's so frustrating because they're not tackling the chemistry. If they had looked at the alkaline salts, the salts end up collecting towards the surface. That desiccates the concrete. When you desiccate the concrete, cement will not form. Once it drops below 80% relative humidity, cement formation stops. So why they're not putting 2 and 2 together, it's just absolutely mind-numbing to me that they're not doing this. So another correlation, that's what we're going to start finding as we start curving into newer concrete. They were doing these studies globally where they had a more sophisticated method of measuring the concrete, where they embedded these relative humidity devices along with thermocouples. Now they found that concrete in the field, when they're trying, even with the water cure, within 2 to 3 weeks after placement, the relative humidity in the first inch or so of the concrete would drop below 80%, even though it had water on it. Then they're showing that there's basically becomes, I don't like the way they explained it, but they said it causes something that doesn't allow the water to penetrate. Well, it's called dynamic equilibrium. That's the same thing that the flooring people are dealing with. So you have that salt collect there. It's not going to let, what happens, it saturates, but keeps the relative humidity low. Because if you take a saturated solution, say of sodium chloride, just table salt, no matter how much water is in it, if it's a saturated salt solution, the relative humidity will stay at 75%. Well, you can't form cement. And the alkaline salts in concrete are even more aggressive than that. They can actually bring the relative humidity down below 70 and 60%. In some cases, I've seen 50%. Well, once that happens, the damage to the surface of the concrete is irreversible. So by following current standards of curing practices, we cannot give a customer a good concrete like we did in the past. It's not as good as it used to be. We have to change our approach to curing. Really, so the only method really that I've seen is if they start making self-cure concrete. Because the studies, even the ones where they use like absorptive aggregate, which is ironic because absorptive aggregate used to be considered bad, and they were discounted and berated. Don't use that stuff because it adds to the water cement ratio. Well, now they're finding out that doesn't happen. It's actually reserved for moisture that replaces the water that gets consumed during the initial cement hydration, and replaces the water that's being used up and keeps the humidity higher, so they get more cement formation. But it's too inconsistent because it's captured in the aggregate and it's not well dispersed through the concrete. So they're finding other issues where they're starting to have, if it's dispersed poorly, what will happen is they can get restraint areas through the concrete, and it can actually, a half-assed job like that can actually create more problems than it solves. So again, this older concrete, the mistake is, it's a big sponge. Water soaks in and then it dries out. Well, with sponge, doesn't have any chemistry going on in it. Concrete has all this chemistry, and the salts are constantly moving, which is why hysteresis occurs. Hysteresis basically is kind of the opposite of diffusion in a way, because what will happen, diffusion, what concrete will do, especially in a lab setting, it allows moisture in, allows it out, allows it in, allows it out. What happens with hysteresis, it allows it in, but hangs on to it for a while. Then slowly but surely let it go. And the older the concrete gets and the more dynamic the environment, the farther apart these go. So the diffusion models that are constantly used in these studies no longer are accurate. So we keep repeating these same tests, these same studies that don't help us. And we keep getting the same results and they don't match up with what we're seeing in the field. Yeah. So I get so frustrated dealing with this, because if you're going to do a study, if you ignore the chemistry in the concrete, why bother? Because it's, the essence of insanity is doing the same thing over and over and expecting a different result. And that's what we've been doing for 70 years.
Yeah. When, just going all the way back to when you were talking about the 40-year-old warehouse and they went and grinded off this whatever was on the surface, right? They were grinding it off for what purpose?
Yeah, we're not sure if it was, to grind it off because it was a curing agent or it was highly polished. They think it was a curing agent because when they would put water on it, it would just sit there, it wouldn't wet.
Okay, because they were going to go in and put something else down. Yeah. Okay.
They wanted to see also if the moisture testing would be affected by the presence of the curing compound. I told them, do not make that generalized assessment off of that, because that's not an accurate way to do it.
Okay. So what was your, I guess, solution to that? So they ground off the curing compound or whatever was on there so they could put in on the new material, but the new material required a certain moisture content, right? Below the moisture test to be below a certain amount before they put the new product on. Yeah. So what was the solution to do that?
There are actually a couple ways of doing it, and I tell them it depends on how high the initial rate is. One of the things I pointed out said this shows you the procedures, how poorly executed they are, because I used to be fooled by this as well, because I thought you grind it, you let it vent. For 24 hours.
That's quite an eye roll, Bob.
Yeah, then you do your moisture test. That'll be accurate. Well, no, that's not true. Look what happened. So if they'd waited till the next day, I don't know what the moisture level would have been, but they would have assumed it originated from the concrete, not from the air. So it's really important to get your baselines. And people are not establishing an accurate baseline in at least 99% of the tests I've seen, not even in the studies. They're not establishing a proper baseline. So what happens with that is if it's not too bad, what I like them to do is test it, grind it, test it again immediately, wait at least an hour and test it again. Now, if it's not climbing rapidly, you're in good shape. There's not much you have to do. But if it's climbing rapidly, you have to you do the moisture test, grind it down some more, and test it again. Now, if the rate of the moisture increase is very slow, you're probably in good shape. But if it's still going, you're going to have to probably shock blast it and put an aggressive blast on, like that epoxy company does. They just say, screw it, we'll just blast it and we're not going to deal with it. because they didn't want to go piece by piece. But with some of these, you don't want to blast a lot because it's a sensitive environment and you want to try and grind it with HEPA filters and all that. But another combination I found works really well, and I stumbled across that. That's not some brilliant idea I had, because I walked into this project and there are blisters on the epoxy, but there were other areas where there are no blisters. Well, wherever there were no blisters, they had a trowel down. So then I started looking at that. We did an analysis and we looked at a few other floors, and we decided to do this combination of where they ground it down. The moisture pickup was very slow, if at all. They put down a trowel down, which would allow diffusion not only of the moisture, but also the salt. So it would allow the epoxy or the adhesive to properly set and cure before the moisture got there. Because once you set and cure and they're not invaded by the salt or moisture, no matter what, they said, well, it's going to come back up again. So what? That's the reason why it stayed down for 40 years. But once we open it up, we expose it to a new moisture source. All we're doing is we're bringing it back to where it was. So yeah, the floor will stay down, the adhesive will stay down. We just need it controlled long enough to allow the adhesive or the coating to set and cure properly, because they're really durable once you do that.
So the two solutions are, one, you shot blast it, which takes off the portion of the concrete that has the salts in it, or the second solution is that you control the environment to a point where the moisture is no longer being drawn to the colder concrete, which is why there's moisture on there. So you control the environment so that stops occurring just long enough for you to do the application. Is that right?
Yeah. Yes. And then, and in this, I found another one where they were applying this, and these are two separate jobs. One, they were applying this epoxy, and the epoxy started bubbling, having failures. Well, they removed it and put it back down again. They were having failures again. So I said, well, did you do an environmental analysis? They said, no. I said, well, do an environmental analysis. So they gave the temperature and relative humidity of the room, temperature of the concrete, and with an infrared thermometer. And then they tested the moisture, and it was all within acceptable range. And I said, well, what's the temperature of the epoxy? Well, it turns out the epoxy was really cold because they were storing it outside, bringing it in, mixing it, and putting it down on the concrete. Well, when you put a cold material down, it'll pull water towards it. The epoxy actually attracted the moisture from the underside from the warmer concrete. So they said, are you sure that's what's happening? I said, well, yeah, let's go warm it up. So I had them put these blankets on the epoxy buckets. They warmed it up to room temperature, did it again. Nothing happened. So they go, that was it? We thought it was a moisture problem. I said, no, you put a cold product down in a warm environment. I said, it's worse when you put down an adhesive because now you create a bond breaker sandwich. So it'll pull moisture from the underside and from the surface. So then when you put your floor down, got too much moisture in the adhesive, too much moisture on top of the adhesive, you put the floor down, it's going to fail. I mean, those are fundamentals that we're not dealing with.
Yeah. So the temperature of the concrete, the adhesive, and then above the adhesive all need to be same temperature.
Yeah, or as close as possible. And what you want to do is, and now they talk about, well, relative humidity, blah, blah, blah. The only relative humidity that's important at the surface is make sure that you're at least 10 degrees above dew point. If you're at least 10 degrees above dew point, it's not going to fail. Mm-hmm. You know, they try to make it look so scientific. It's just, no. If it causes dew on a leaf or a surface, then you got to take care of that. Now, the other thing, and this is what's so important, that salt on the surface, because I'm going to go all the way back there. The salt on the surface, that is a hygroscopic salt. Everybody keeps talking about dew point, dew point, dew point. There's two types of dew points that we're dealing with when we're dealing with concrete. That's atmospheric dew point, which when it starts approaching 100%, things can get wet. Now you can see things getting wet before 100% if they're hygroscopic. So glass and surfaces like that can actually start getting a layer of a film of water on them even before atmospheric dew point occurs because of the strong attraction it has. So when people say, is it that strong? I said, well, yeah. I said, one of the good examples I like to give, because the siliceous, it's SiO2, it's just silica. Well, so is glass. Glass is silica. So I use that as an example. I'll take two lenses that you use for microscopes and put a drop of water in one, stick them together, and I tell them, okay, pull those apart. They can't do it. They can slide them apart, but they can't pull them apart. The attraction of the water is so strong to the surface, it clings and acts like a glue. So it's hanging in there. So if you have those salts, that attracts even more. It hangs on to the moisture.
Yeah. But the salts are, if we're talking about newer concrete, how long does it take the salts to accumulate on the surface?
With the older concrete back again, prior to 2002, I would say that it would probably take at least 5 years to be even a minor problem. But 10 years and older seems to be like the real area there where you start having problems. So all concrete prior to 2002 is over 10 years old now. So
Yeah, way over.
yeah, way old. Now, what I wanted to talk about with the salt accumulating, that has an ionic dew point. It has a dew point, so like I explained earlier with the sodium chloride, depending on the salts, it will attract water at maybe 60% relative humidity, 50% relative humidity. We don't know. So it can accumulate and start getting damp. And we don't think it's damp because we're not even close to atmospheric dew point. People get tricked by that.
Yeah.
That's why you got to take that salt off the surface. Because if it's doing that, even though it looks dry, and if you use a relative humidity probe, that doesn't tell you squat because this is all at the surface, but you can find it out with a moisture meter.
Yeah. Oh, I guess the reason I'm asking the question is with newer concrete, if I circle back to your original story about the guys grinding off whatever was on the surface of that concrete and that exposed the salts to draw the moisture to the concrete. If we're talking about newer concrete, the reason why I asked you how long it takes the salts to get to the surface is if you put down new concrete, what we're seeing, especially in data centers and warehouses, is there's a lot of use of hardeners. So they're putting down this hardener. If the one manufacturer that pops in my head, I believe they say you have to wait 28 days before you put it down. What I was wondering is how long does it take for the salts to reach to the surface of new concrete? If it's longer than 28 days, is I guess there, in theory, is these hardeners stopping the salts from getting to the surface, I guess, is what I was getting at.
Well, that would have worked with older concrete, at least to some degree.
Uh,
I'm glad to hear that. They wait 28 days because some of these nimnods put it on the day after or the day of the pour. No, don't ever do that.
yeah.
But the problem is there was between 2002 and 2018, the EPA kicked in a requirement where the cement manufacturers had to gradually come to compliance, and that's why it took such a long window of time because they didn't want to put them out of business. But they had to comply where they were recapturing some of the flue gases to stop CO2 and all this pollution that the cement manufacturers were putting into the air, and it's called CKD or cement kiln dust. Cement kiln dust is extremely alkaline. Now, it varies from plant to plant because your local resources, some aggregate is more alkaline than others. That's just regional. That's just the way it is. So some will have a more severe problem than others. So you can't take, a nice, neat package that this is what we do all the way across the country. Now, if you go worst case scenario, it's too expensive. But if you go optimistic, you're going to miss things. So what's bothering me is the cement producers are not coming clean with this. Because I asked them, said, what is your CKD in your cement? And they wouldn't tell me. I said, look, well, I didn't sign an NDA, but if we're going to compensate for this, I have to know what the content is. But if you're not sharing this with me, it's a big guess. Cement kiln dust is so alkaline that during the curing process, which prior to this, near surface alkali silica reaction was an issue, it's more of an issue now than it ever was because there's now more alkalinity. Now, the alkalinity where it's really, really bad is sodium hydroxide, which is the main alkaline component of the cement kiln dust, suppresses the solubility of calcium hydroxide. By suppressing the solubility of calcium hydroxide, what it does, it inhibits the formation of additional cement. So here's where the chemistry is not being addressed in these studies. They're wondering why this self-desiccates so much, and they're blaming the cement. Well, no, the cement formation will consume some of it, but not all of it, because you have technically enough water in there, even with a very low water-cement ratio, to hydrate all the cement. The reason why it can't, and especially if it's warmer, what will happen, the heat will trigger that, and you get a spike where you get a rapid formation of cement, then it drops off a cliff. It drops off a cliff, a combination of heat and alkalinity. Heat and alkalinity both suppress the formation of cement. They both do. Alkalinity creates an artificially low, I can't say artificially, but it lowers the relative humidity. So that's what's causing the lowering the relative humidity in the top inch of the concrete, is this new alkalinity. So does it affect the concrete? Immensely. I saw a study done by the Texas Transportation Institute, and this is fairly recent, I think it was 2014, where the concrete was 4,000 psi. They water cured, they did a 7-day water cure, and this is in a lab. They did a 7-day water cure and then an air cure. I'm not going to address the air cure, only the water cure. 7-day water cure, nobody does because you can't spend the resources on it, and the water, that's considered a waste of water. But what they did is they went ahead and did the 7-day water cure, but they found that the surface was still self-desiccating. Not to the same extent that you see in the field, but it was still dropping. It got close to 80%, and then eventually dropped below that. But after a couple weeks, it got close to 80%. 80% is the bare minimum to form cement. That's too slow, and you're going to get an inhibition of the cement formation. So what they did is at 28 days, they did a compressive strength test of the concrete, 3,000 psi. It was fine. However, he sliced off the top inch and was a full 20% lower in compressive strength. Why? There's not as much cement. This is not a uniform homogeneous material. So if you start correlating what we're seeing with the salts, the self-desiccation, the near-surface ASR, all the evidence points to this alkaline salt collecting in the surface, and we're not addressing it. If we address the surface, let's say you put in something like a colloidal silica. A colloidal silica, in my opinion, is being presented incorrectly, or incompletely, I should say. They show how it acts like a pozzolan, reacts with calcium hydroxide. Well, yeah, it does. Now, so do other pozzolans. But what happens if it self-desiccates and the calcium hydroxide doesn't form? The pozzolans don't do squat, especially a dryad. Now, colloidal silica is wet. It adds water to it every time it reacts, so it's replacing its own water. It reacts with this, and then gives off its water. However, if the alkalinity is high enough, I don't think we'll get a consistent result. So if we know what the CKD level is in the cement, you can compensate by adding more colloidal silica. Now, the colloidal silica, what it does is it will react with the sodium hydroxide and convert it to sodium silicate. Well, that's okay because the sodium silicate is not an admixture. It's already in there, and the volume and the setting of the concrete have already established themselves when this starts to react, so it doesn't thicken the mix. But what it does, by reducing the sodium hydroxide, it stops the self-desiccation of the concrete surface. Because I saw a study done by Purdue in the surface, and we have to take this with a grain of salt because they did this in a laboratory, but the surface is actually denser than the remainder of the concrete. I honestly didn't think that was possible. So there are ways, and it's not just colloidal silica, there are ways of creating these admixtures that don't cost a lot of money. In fact, it's just management of moisture. Don't cost a lot of money, but they can create a self-curing concrete. We don't have to put water in the concrete anymore. It becomes self-curing. We get rid of that weakened layer. And I will tell you right now that I guarantee that all these problems are having with things like type 1L cement and the curing issues they're having with elevated temperatures, those are going to go away. We're going to have really good concrete. It'll probably last at least twice as long as conventional concrete and probably last longer than the concrete they were placing in 1920. We'll have really durable concrete because that durability goes across the board. Because if you look at weathering characteristics of concrete and durability, it almost always starts from the top down. It doesn't come from the bottom up, it's top down. Bottom up is usually subsidence or frost heave or something else like that. It's not the concrete itself. Most of the weathering durability issues we have goes from top down. ASR starts there, all that.
So going back to my original question, I think you might have answered it in there somewhere, but I might have not caught it.
Sorry, I didn't want to.
I know you gave the answer to our third item that we wanted to cover, which is the differences in today's concrete versus the older concrete and why we can't cure it like we typically do, which is a chemical application. You spray it on, or yeah, that's normally what we do. Because like you said, no one does wet cure anymore because it's just the logistics and the cost of it is cumbersome, especially in today's environment of concrete construction where you don't want things to slow things down. So you want to build these things fast, get the other trades behind you. So the wet curing is just not feasible. I do see it though on water treatment plants, pump station type jobs. So they do have it still on that, believe it or not. But anyways, so going back to my question is the maybe we're just masking or covering up the salts that are coming to the surface when we're putting down a hardener at 28 days. Is that something that could be happening?
Well, I think
Because what I'm hearing is these hardeners are specified and very common companies that that are out there that build big warehouses and they build data centers. The hardeners are specified. There's got to be something out there that the engineers are seeing that there's a reason why they're specifying these products. There's got to be something out there that says, hey, this is giving us a durable surface, a durable concrete. That's why we want it in our specifications.
Depending on the chemical makeup of the hardener, I don't like the alkaline silicates as a hardener because if you have cement kiln dust in there, it's going to add more sodium ion to the mix, and you don't want to do that. Lithium silicate is a good hardener for that, and so are colloidal silicas. Those, I think they're probably the predominant hardeners that are being used today, and I have no problem with those. So if all you're doing is hardening the concrete, that'll work great. You just can't put anything on it.
Yeah, I do.
On it afterwards, you'd have to go through what you did before and just shot blasted, get that salt out of there, and basically treat it like an older piece of concrete.
Yeah, and then your comment about you were glad to hear that they're waiting for 28 days. I haven't been part of a project that's done this, but I've heard people putting the hardeners down before the 28 days, actually after the concrete is placed, and they're using it as a cure.
No. Don't do it. Even in lab study, I saw this study done with metakaolin, which is a type of plasmon admixture. It was shown that the normal development of calcium hydroxide took anywhere from 5 to 7 days to develop in a lab setting. In a field setting, it could be nearly a month before it all forms. At least, we're substantially formed. And you do have to wait for that for the hardeners to do you any good. Now, the lithium hardener and the colloidal silica probably don't have to wait that long because they will do things independently. I call lithium silicate a forgiving one, and I call colloidal silicas the patient ones because they'll sit around and wait for the calcium hydroxide to form, then react. Because they're pretty selective about what they react with, because they have to react with an alkaline component. Because if you take colloidal silica and mix with sodium hydroxide, it'll make sodium silicate. So it changes it to something that's a type of hardener. It'll secondary hardening as well. So, and that kind of a sodium silicate, you're not adding more sodium to the mix. If you're spraying sodium silicate on there, you're just compounding the issue. So I don't like that. But with the lithium or the colloidal silica, you're not compounding the issue. You're restricting it.
Okay. All right. Well, I think we hit on the 3 things we promised that we were going to talk about today. Is there anything else you want to hit on before we go?
Are also additives used for cement grinding that are creating complications. And it was nice because it was acknowledged on LinkedIn. I brought up the issue about issues they have with the grinding aids, and it prompted quite a bit of discussion because the grinding aids that they use now that are the most efficient are glycol-based and amine-based. Well, those don't go away. Those don't exhaust. I'm not sure how much they put in there. But what happens, Sika, I'm going to give him credit for this, Sika out of South Africa, this gentleman was doing a study on it. He was looking at this decorative concrete, and the cement grinding aids were reacting with some of the aggregate in the concrete, creating a liberation of the iron so that it was floating to the surface. It looks like a bunch of rust spots on the concrete. Now, that's unsightly for decorative concrete, but what's that doing underneath a coating? You don't want iron under a coating, under any circumstance. It's going to change a lot of things, and besides debonding and creating issues with future coatings, that we're just not being told this, because as I did more research, I found that the cement producers are not required by law to divulge what they put in their product. That is ridiculous. The ready-mix producers are required by law to divulge what they put in if it's not sand, water, cement, and aggregate. If they put anything else in, they have to divulge it. If they just give you concrete, they don't have to divulge anything. But I think it's unfair that they get saddled with a product they don't know what's in it, and they can have things go wrong, go south on them. Concrete contractors have things go south on them, and they get blamed for it. Well, I saw I revisited a problem they had up in the northeastern portion of the United States where all this carpet tile failed. And they blamed it on plasticizer migration, and the manufacturer got nailed. Well, and they were showing the alkalinity of the concrete was contributing to it, blah, blah, blah. Well, as I started looking at in hindsight, they never tested for amines or glycols, even though they were in there when I looked at the mass spectrometry where they were doing the chemical analysis. Those were in there. They didn't identify where it came from. They just assumed it came from the backing of the carpet or something in the liner, the adhesive it had or whatever. They just blamed it on that. That could have originated from the cement, but nobody bothered to look because they were never told. This information is not being divulged. And that, we have to all come clean so we know what we're dealing with. Otherwise, people get thrown out under the bus that didn't do anything wrong.
Yeah, or come up with I don't know, if there's a test out there that we talked about on, I think, a couple podcasts, is how you can test your cement when it comes in. So before putting it, utilizing it, you could set up essentially a quality assurance or quality control program to test your cement, and so that you do know what you're dealing with. But on the other hand, I think, I think your concern is beyond, fair to say, beyond a 28-day strength, because that's what we're all concerned. That's what the concrete ready mix supplier is graded on, right? He's got sometimes a 3-day, a 7-day, and a 28-day test that he's got to show that he's met a strength. So I think your concern is beyond that, and it's difficult for us to think about what could be down the road for the concrete being blamed for, I guess.
Well, yeah, because the workmen get blamed because they're not chemists, they're not scientists, they're skilled craftsmen. They should be allowed to do what they're doing without having to look over their shoulder every time they put something down. And this really irritates me. What you're talking about with your cement quality control, I would love to see some of that and give feedback, because I would have a different perspective on that from a chemical standpoint. Because like you said, all the emphasis on 28 days. That is the worst benchmark for quality concrete, the worst. Because the higher the 28-day is, especially with warmer temperatures, it means your concrete's going to be weaker in the long run. Correlations are always there. One of my favorite whipping boys is to show the surface absorption of precast concrete. Precast concrete that's steam cured, if you sit it side by side with a piece of concrete that you placed with your company, if you put them side by side, if you throw water in your concrete, it'll dampen the surface and gradually go in. But if you throw the same amount of water on precast, it'll disappear. Throw it on there again, it'll disappear. Throw it on again, it disappears. Why? Because there's no cement on the surface. It's really permeable. But that heat destroys cement formation. So inside the precast, it's really durable. Now, if you could take precast and sacrifice the first inch, you would have one incredible piece of concrete. So if you over-designed it, say by 2 inches on either side, and considered the gradient as like an icing around a cake or something, remove that icing and expose the cake. You'd have an incredible piece of concrete. But we don't do that. So it soaks in, carries in things that are not supposed to be in the concrete, and starts the damage in the surface, and it works its way down. I mean, again, we're ignoring the chemistry. If we start incorporating the chemistry, and this makes sense, we'll know how to compensate for what we're being given.
You're right. Yeah. All right. Well, I think this is a good spot to end today. We went extra long, but there was a lot of good nuggets in there, so I hope everyone was paying attention. Bob, is there? I usually ask you if people want to reach out to you, how do you want to reach out to you? But I'll put your information in show notes. Are you giving any talks or conferences coming up, or anything you want to plug before you go?
That next couple of months, I'm kind of burned out right now because I had 5 in a row.
Okay.
I'm down to 2 brain cells, and they're playing hide and seek.
Okay. All right. Well, we'll like I said, we'll put your contact information in the show notes as usual. And I appreciate you coming on the show today.
Thank you, Seth.
All right, folks. Until next time, let's keep it concrete.
Right.